Okay, next up we have Jordan Furlan from Collins Engineering.
Let's get this started here. I remember when that Montana timber project was going on, it was really interesting to see how they implemented all those repairs now. Let's see, slideshow. Okay, so we'll switch gears a little bit now. Thank you to everyone here for hanging in almost to the end. Happy belated Pi Day. So this presentation will be using 3D acoustic imaging to document deterioration in the Lenore Bridge. Just quick background on me, 15 years of experience doing various types of inspection, heavy emphasis on underwater inspections and a lot of acoustic imaging in that time. A little background, the outline of my presentation here. I'll start with kind of a brief history of the Lenore Bridge and a sort of an overview of this little project and why we did it. Then I'll go into more of a specific history on the inspection, the various inspections over the years of the Lenore Bridge. And then since this is about acoustic imaging, if you're not very familiar with it, I'll give you some background on sonar, what it is, what are the different types of acoustic imaging, why did we choose the system that we used for this project. Then we'll dive into the actual results and the findings from our acoustic imaging study. Just go over a brief, kind of simple alternatives analysis that we did at the end to determine a course of action. And I'll just end with some conclusions and best practices and lessons learned from this. So we'll move right into the history and overview part of the presentation. So here is the Lenore Bridge, larger this time, so we can orient ourselves so you understand what I'm showing you further on in the presentation. So north here is roughly on the right side of the image. The bridge it's at a slight skew, but we're calling north the right side. The piers are numbered from 1 through 4, from south to north. And the Clearwater River here flows roughly from the east to west. So the piers, Pier 2 and Pier 3 in that image, kind of in the channel, those are the two piers that we're going to be concerned with for this presentation. So this bridge is Lenore Road over the Clearwater River in Nez Perce County, Idaho, in Lenore, Idaho. It was built in 1935, it's pretty old. About 30 years later, they did a rehabilitation project on it in 1965. The approach spans are Warren pony trusses. The main span in the middle is 2 built-up plate girders. It's 5 spans total, about 530 feet long. 4 reinforced concrete piers located in the channel, and they're spread footings that just bear on bedrock. Average daily traffic's not that high, about 400 vehicles a day. So this bridge is in poor condition, so there's areas of significant concrete section loss below water that we'll see more in the later slides. It can be a challenging bridge to dive depending on the conditions due to the very swift current at the bridge location. So the need to get good measurable data on the areas of section loss is what necessitated this sonar study. So for the history buffs, I know Shane on the first day talked a lot about history. This bridge has a long history as well. If you're very observant, you might have noticed that the picture on the first slide only had 1 truss span on the south side and 2 on the north side. And the elevation view on the bottom of the previous slide showed there was 2 originally. In this photo from 1956, you can just see the original first span still there. At some point in time that I'm not exactly sure when, they must have removed that first span to either widen or construct US 12, which runs across the south side of the bridge. Another fun fact for the history buffs is that Lewis and Clark actually passed by this bridge and, the location of the bridge in 1805. Camped not far away in Orofino, Idaho, which is actually where we still stay today when we inspect this bridge, so we're kind of walking in their footsteps still. Furthermore, the Clearwater River here is the largest tributary to the Snake River by average discharge, and the Snake River is the largest tributary to the Columbia, which is how Lewis and Clark actually made their way to the Pacific Ocean where they ended their journey there. So we'll go into the kind of the specific inspection history so you understand kind of what necessitated this little study that we did. So the first records we have of the scour and section loss of this bridge started back in 2007 when the state was doing its own underwater inspections. I'm sure it was known about before then. They were diving it before then, but the records are kind of sparse. The problem was that the defects on this bridge they're kind of being characterized as a scour of the footing issue, but no one was really sure how serious it was because it's kind of hard to inspect. There wasn't a lot of information. Since there was confusion about how much of a threat the scour and/or section loss was to the bridge, we decided to do an in-depth inspection and to take a look into the history of the bridge to kind of figure out what was going on. So 2007, they were noting, footing exposure and undermining on those piers 2 and 3. 5 years later, 2012, the notes were kind of the same, just expanded a little bit, clarified, built upon. In 2017, then again, we kind of decided to change that undermining to just call it concrete section loss, but the encasements, we're still calling those footings. Then in 2008, we decided to do this special inspection to kind of investigate that further and determine an appropriate plan of action and address any maintenance issues. And then inspected it again just last year, and things were stable since the previous. So the only thing we're doing is recommending an inspection month change. So what we found when we dug into the history of the bridge a little bit, I think we might have had to go to microfiche for this, was that what previous inspectors were calling footings were really large concrete encasements that had been constructed sometime in the mid-60s. That was that 1965 reconstruction. So that's really when we recharacterized the defects from a scour undermining issue to more of a concrete spalling section loss issue. Similar mechanism was kind of working, but instead of the channel bottom scouring away, it's now the concrete that is deteriorating instead. So the question became, how bad is this current section loss, and is it starting to undercut the original bearing area of the bridge? So we'll kind of stop on the bridge for a second. We'll move to acoustic imaging to just give you a quick background on that so you understand what I'm talking about. So if you don't know, sonar stands for sound navigation and ranging. This image here on the slide is what most of you probably think of when you think of sonar. So it'd be like a single beam of sound generated from the vessel that returns a depth reading like the fish finder in your boat, measures the time the sound wave takes to bounce off of a target and return to the source, typically produces a cone-shaped sound wave, and the pulse is strongest directly below the transducer, and it weakens as the angle from the central axis increases, so you're usually getting a return from what's directly below you, and you can get false returns from something on the edge, which is what it's kind of shown in this picture here. So next up is multi-beam sonar, which some of you might be familiar with. So rather than a single beam, multi-beam contains many rows and columns of narrow beams that are insanifying a volume. So this matrix of narrow beams allows for more dense data coverage, creating hundreds or thousands of data points with a single ping. So some benefits of using a system like this is that it creates a 3D image of the object you're trying to scan. It does have a high degree of accuracy and precision. It does have some limitations still. It can't see past obstructions, so much like shining a flashlight in a dark room is the analogy we usually give, it will create shadows. If it's mounted to a vessel, it has trouble seeing things like undermining due to the angle of attack of the sonar beam. It can't see under things. I'll talk about more about in later slides. And it does create large amounts of data that can be cumbersome and time-consuming to process. So it's something to be aware of when you're using multi-beam. So for this project, what we ended up using is the Teledyne BlueView BV5000. So why did we select this system? It's portable, it's lightweight, it's what we call sector scanning, which means it will actually move itself around. It has 256 beams and a max range of about 100 feet. This equipment can do a full spherical scan with its 256 beams, so it'll generate point cloud data with millions of unique XYZ points. It can be connected to motion compensation and a total station to be fully geo-referenced and not just referenced to an arbitrary datum, which we did for this project. Since what we were trying to see was located at the base of the piers, we actually had to fabricate a special low-profile plate mount so it would sit right on the channel bottom in order to gather the data that we wanted. We also combined the sonar data with above-water photogrammetry to create a fully realistic 3D model of each pier that we were investigating. So here's a slide of the blue view in its most common tripod-mounted configuration. This is usually the best for performing bottom scans or the vertical faces of structures. A limitation of this one is that it doesn't perform well in heavy current, like at Lenore, because it'll just fall over unless the legs are heavily weighted, but then it's pretty cumbersome to use. So it'll also have trouble seeing beneath structures such as a bridge footing or something like that, where you might want to see the extent of undermining. So that's why this configuration was not chosen for this project, even though we do use it a lot on other things. So this is the blue view in its probably second most common configuration, which is mounted to an arm attached to the hull of a boat. With this configuration, you usually want the full GPS and motion compensation to account for the movement of the boat. An advantage is that you can cover a large area quickly, which is great for hydrographic surveying, which you can use this system for as well, but it takes longer to set up. It requires more in-depth knowledge of surveying practices than most engineers usually have. You can still use it without motion compensation in this configuration, but you must keep the boat perfectly still during the scans, which is possible, but only in very calm water, and it's definitely not ideal for something like Lenore Bridge, where, again, that you have the angle of attack issue where you're not really going to be able to see undermining or something like that in the pier. So on to the final configuration. I wish I had a slightly better picture of this, but this one was taken looking down from our boat through about 10 feet of water at the sonar at Lenore Bridge. So it's basically sitting on a metal platform that keeps it just above the surface of the channel bottom. So this is good for high current situations because it's much less likely to be pushed over, and it's low enough to see undermining and defects at the base of the piers, which is what we were most concerned with. So we only had to put some pieces on it to kind of stabilize it and a little bit of weight to just keep it in place. It worked out pretty well. So these are the two piers in question again, piers 2 and 3, as seen in the previous overall photo of the bridge. So the flow looks calm here, but it's actually very swift, and it only looks that way because of how laminar the float is in this location. There's not so much as a ripple normally, but the flow is extremely high, which makes diving it challenging. It can be like getting hit with a wall of water when you're down there. So we opted to use sonar to increase safety and get more detailed information. It's diveable, but it's much better when it's supplemented with sonar. One thing to note, the tree trunk wrapped around the upstream nose of Pier 2 there in the left picture, that's actually a tree. It's unusual how perfectly it wraps around the nose there, but we'll see more of that later. The encasements that we're trying to investigate here are actually just below the water surface because the water is up a little bit. So you can kind of just see it below the water in the Pier 2 picture, and I'll share more details in the following slides. One thing with sonar, like with diving, you usually want to dive something at low water because it's easier and then you can see things that are above water. Sonar, it actually helps if the water's up a little bit higher because you have more room for the sonar to work and to scan and do its thing. So now we'll move into the part that everybody's waiting for, the actual results of the acoustic imaging and how we put it all together. So here's a look at the same pier with a combined sonar and above water modeling. These are isometric views of the north and south faces of Pier 2. So the channel bottom here is in green, and the red parts are slightly higher in elevation than the rest, and the black areas are actually acoustic shadows where rocks or some other obstructions were blocking the sonar beams. That's the flashlight in the dark room that I was talking about. In this image, you can just make out some voiding at the interface with the channel bottom, but it's kind of hard to tell with all the acoustic shadows, which is another reason why it's good to supplement a sonar inspection with diving if possible. There is that same tree that we were able to model that's wrapped around the upstream nose. Turned out pretty well. This is actually the encasements that were just below water, so that's what we were interested in for this study. So we'll move on to a little bit more about that. And that's just pointing out the channel bottom right there. So here's what it really looks like for comparison. These are pictures of the voids in the encasement located at the interface with the channel bottom. So the channel bottom is smooth bedrock for the most part, and the concrete has been worn smooth from years of water erosion. It almost looks like rock. Details this small can be hard to discern from sonar data, even with something like a multi-beam, especially when you have a rocky bottom that causes so many acoustic shadows, but something like this would be immediately obvious to a diver. But since we have this image for comparison, then it helps make more sense of the sonar data. So this is the same pier, but now we're looking straight down in a plan view. You can see the tree again. Upstream is on the lower right side of the screen. The black circles, there's the tree. Black circles right there are actually where we did the individual sonar drops. So we had to physically drop it all around each pier to get a full scan around each one. So we had to take it, tie up the boat, throw it in the water, get it in position, do a spherical scan, check the data, pick it back up on the boat, move, drop another one, and you can see how we did it all around the pier. The sonar doesn't get the location directly underneath the unit, so that's when you get those nadirs in the data. It's called a nadir, and it makes that black circle. So you can overlap the data with the other scans, but you can usually still see artifacts because the data is so dense that close to the sonar head. And this box here is another area of interest that we'll investigate in the next slide with this encasement. So this is a detail of the feature highlighted on the previous slide. This is the downstream nose of Pier 2. So this was previously called out as concrete section loss, but when you examine the sonar data, it tells a different story. We think it was possibly some kind of overpour or blowout in the formwork back when they were doing the rehabilitation back in the 60s. The sonar image is on the left, and the photo for me is on the right for comparison. So it's kind of hard to see on the slide, but it is dimensioned. We were able to create some very accurate dimensions for this defect from the point cloud data that then we can use to monitor these in the future. So these are the isometric views of Pier 3 now. As you can see, they look similar to Pier 2. The pink, which you can kind of just see on the pier nose, is actually some timber debris that we were just able to pick up. Something spongy like wet timber doesn't typically return sound waves super well, but we were able to pick some of that up. Pier 3 also has a large area of section loss at the downstream nose. That's the timber right there. And that's another one of the defects that we were trying to investigate with this. So again, plan view of Pier 3 this time. You can see the timber debris at the upstream nose still. Area of interest again here at the downstream nose in the red box. So we'll talk more about that defect on the next slide. So this is a close-up image now of the large void located at the downstream nose of the pier that was previously labeled as scour. So we measured it from the sonar to be about 4 feet deep and over a foot high. So pretty significant. Instead of scour, it was most likely due to poorly consolidated concrete when these encasements were poured, and the vortex shedding action from the current at the downstream nose, just eroding that away over the last 60 years or so. So as you see, you will see there is some reinforcing in it, but it doesn't seem to be keyed into the actual bedrock. And as you can see from the image on the left, we were able to determine from the sonar data that the section loss isn't quite deep enough to be directly undermining the downstream column of the pier yet. So when you look down at it there, you can actually get a pretty good idea of its extents in the relation to the rest of the substructure. So here's the photos of that now. So for comparison to the sonar, again, here are 2 photos that I took of the void at the downstream nose. Note the rebar protruding from the bottom. That doesn't seem to be keyed into the bedrock anyway. And this void is actually large enough for me to basically swim under it to hide from the current and get a little rest while I'm diving. So it's actually a handy little feature for this pier. Helps inspection. Okay, so we did a basic alternatives analysis. I'll go through that now. Basically, the first option was, do you reconstruct the piers? You know, it's the best long-term result. It'll restore the bearing, fill in all those losses of section. Obviously, that's going to be the most expensive, probably require permitting. They'll have to work in the river. It'll be a whole thing. Option 2, do some sort of scour repair. Could put Ajax would probably work pretty well here, or grout bags. It would protect that encasement from further deterioration. Should be stable during high flows like they get there. Won't restore the loss of bearing. It'll still be fairly expensive, probably have permitting. It might affect the profile of the flow in the river, so not a great option. Skip to option 4. That was just do nothing, leave it on the 60-month inspection cycle. Lease inspection obviously doesn't address the problem. What we settled on was simple, just increase the inspection frequency. Since we figured this probably wasn't a real critical issue to the bridge, it was probably better to just try to monitor it more frequently, and since we weren't really concerned about stability. So this saves a lot of money not having to do a reconstruction, but kind of kicks the can down the road a little bit. Basically, the superstructure is kind of controlling this bridge anyway, so it didn't make a lot of sense to do a ton of work on the substructure. So I'll just end on a kind of combination of conclusions, best practices, and lessons learned for the final slide. So acoustic imaging can be a powerful tool, but it's still best used in conjunction with divers because it can't see past obstructions, like I said, can't tell you the type of material that you're looking at or discern really small scale defects like small areas of voiding at the interface with the channel bottom. It gives repeatable and quantitative data if you understand the capabilities and limitations of the machine that you're using. It increases safety by being able to determine potential hazards before a diver even enters the water, like that timber debris. You want to select the right system for the job based on what data you're looking for. There are many different types of sonar, and this one might not be the best for every situation. I didn't cover some of the other ones, but depending on the situation, a single beam or a 2D sonar system might be better, which we use a lot depending on what's going on. And you want to make sure that the system is configured in such a way that it can get what you're looking for. If we had gone out there with a boat-mounted or tripod-mounted configuration, we never would have been able to scan the features that were close to the channel bottom that we were looking for. So since the study was undertaken, Nez Perce County recently replaced a very similar Cherry Lane Bridge, which is just downstream from Lenore, and they have also received grant money to do a feasibility study for replacing the Lenore Bridge as well. So hopefully that'll happen soon. So that's my presentation. I'd like to thank Dan Gorley, the Idaho Transportation Department, and everyone here for attending. Thanks.
Any questions?
The preceding was produced by the National Center for Pavement Preservation. More information can be found on the web at pavementpreservation.org. Additional support provided by Michigan State University.